Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you have chosen to join us today. Let's go inside. The lecture's about to begin.
All right. I have a question for you as I welcome you to this first distinguished lecture of this academic year. The question is, what is the most fundamental synchronization primitive you have learned while you've been here in the Computer Science Department? Answer, when the cookie queue ends, the lecture begins. So here we go. Today we're very fortunate to have Professor Chuck Seitz from Caltech to join us. And in the tradition of these lectures, I'm going to give you some background information on Chuck, which you won't find in any biography in a journal. I had a chat with Chuck, and he very candidly said that he considers himself extremely fortunate in terms of the investment that society has made in him in terms of his education and training. He grew up in what he and I consider a golden era. And in fact, he represents not a generation gap, but a kind of generation bridge. He looks at the people older than he is and recognizes that they did not grow up with computers, and their access to computers came as a severe retrofit in some sense. People younger than he had computers all over the place. They grew up with them in high school. His generation, he had to discover computers as he was, in fact, as his intellectual processes were being formed, and he was young enough to be enchanted by them as a discovery instead of something you find on your parents' desk as you grow up in the bedroom. As a young man, he liked to play games. He built telescopes, did math, liked physics and chemistry, won the Illinois State mathematics competition as a senior in high school. And while I was in high school, I had a chance to play with an IBM 650, a really powerful supercomputer from Northwestern University in 1959 and 1960, before probably most of the people in this room were born. He then went to MIT, and of course he decided he wanted to get a bachelor's in chemistry. He found that that field was just too empirical, so he moved to physics. But that field was too dry, and there had been too many great minds plowing the field and developing all the great principles. So he found computer science, an unmined, fertile territory to which he's contributed significantly. And I imagine that's half the reason most of you are here. It is an exciting field with basically frontiers all over the place. The first course he took at MIT as a freshman was a course as an introduction to automatic computing from one of the lesser-known faculty there, John McCarthy. And Chuck was exposed to the then emerging first version of Lisp. And the notions of recursion and other fundamental principles really began to suck him into computing. The rest of what did it was just a wonderful milieu at MIT. The courses, the faculty, the students, the environment, the games, the pranks, and all the rest. And so he received his third degree at MIT, and his second and his first as well, all in EE. He got his PhD in '71. The title of the dissertation was Graph Representations for Logical Machines. Now, while he was there, he spent some time at a lesser-known small school down the road, Harvard, and in fact at that time began to develop what we now call future virtual reality, just about 30 years ahead of its time. When he graduated, he went to Utah University assistant professor for a couple of years, and spent some time there designing what at that time was the most advanced graphic system around from Evans and Sutherland. Another gentleman in the audience was in that same group, Danny Cohn, sitting right there, turning his head to avoid eye contact. He then spent 5 years at Burroughs and went to Caltech, where he currently holds a faculty position. He went there in 1977. Now, the most important thing I haven't mentioned yet, Chuck is undoubtedly the most talented expert pilot on the Caltech faculty. Okay. And he began his flying experience with Danny Cohn, who was also an expert pilot, and he's promised to teach me, and I've been avoiding it. In the second hour of his formal training, his instructor showed him stalls and spin recoveries. Sounds awful. As soon as he got his license, he began to study aerobatics. And he still practices aerobatics. In fact, the only plane he owns is a dynamic, is it bi or single wing plane? Bi wing. The red band strikes again. His message to you, as forged by his contact and affiliation with people like Carver Mead and Richard Feynman, is the following. Pursue those things that you find adventurous. Why? For the sheer joy and fun of it. Go for the long-range, large gains, not short-term, little incremental improvements. Chuck has followed that philosophy in his entire career. He's well known for at least two very important developments. The cosmic cube, which basically is the hypercube and all the ancestors from there, and the Mosaic, a fine-grained multicomputer, which he's going to discuss with us today. Chuck, I'll tell you.
Only trouble with introductions like the one Lenny just gave me is that I'm afraid I may disappoint you. But I want to show you our latest adventure. My students and staff and I have been working on this for some years. It's been very little exposed in the literature. It's only now we're ready to start publishing papers about it. It's only been in about the last year we've been willing to talk about it in even things like DARPA meetings. Now, some of my colleagues here who have heard about some of this in DARPA meetings, let me apologize to you ahead of time. Some of this will seem a little bit repetitive because I really want this lecture to be for the graduate students to show them a little bit about how we conducted this particular system building experiment. It was really quite an elaborate experiment. It took the efforts of a dozen talented people over a period of about 5 years to pull this off. If any of you want to send me electronic mail, there's my email address. And in way of outline, I'm going to try to tell you what all of the words in the title here mean. I think you should all know what an experiment is, and we'll talk a little bit about what a fine-grained multicomputer is, but we have to start with what a multicomputer itself is. To give you a little bit of the background and motivation for this experiment, including some of what 5 or 6 or 8 years ago seemed like some really wild guesses that guided the initial conception of this project. Give you a kind of bottom-up view of the Mosaic hardware. Here's a picture of a modest-sized Mosaic machine. 2.7 million, 2,700 million instructions per second, 100 watts. That's a pencil by the side of the machine, by the way. That's a real pencil. That's not one of these carnival pencils. This is one that was just happened to be lying around the laboratory. I want to tell you about an embedded system example of this hardware, this atomic local area network that was developed by Danny and Greg and Feldy and some others who are here at the USC Information Science Institute. And then I want to tell you about the programming and runtime system and some future plans for this machine. Okay, so first of all, multicomputer. What's a multicomputer? Most people, have heard about parallel computing and concurrent computing, but A multicomputer is a specific architecture that is composed of a set of computing nodes. Oftentimes they're identical, and they're connected by a message passing network. The message passing network may include some other connections, for example, the local area networks. I know you're all big on networks here, so you'll hear the word network a lot. If you ever hear the word queuing,
It's an accident.
pure accident, yes. Okay, what are these computing nodes? Well, these are quite conventional computers, one or more processors connected through a memory bus to some primary memory, and also to a packet interface, something that allows the node to send and receive or source and sync messages from the message passing network. How do we build the network? Well, of course, we mean here for n to be rather large. If n was something like 1,000, we obviously can't connect every node to every other node. So we have to connect some subset of the nodes. The early machines used a binary n-cube or hypercube connection. The machines we've been building for about the last 5 years use a two-dimensional routing mesh. So in fact, the packet would be injected into the network into a router. So for example, if we needed to go from this node to that node, it would be injected into the network and routed through the network to this other point. That network is regular, by the way, so that we can use algorithmic routing, so we don't have to keep routing tables and things like that around. It's bidirectional so that we can take advantage of locality. That is, it very often happens that we have two computing processes that communicate with each other frequently. Frequently it's a parent-child relationship in say, a search problem, in which case locating them physically close to each other allows us to minimize the use of communication resources. Okay, so that's the structure of the architecture. What do you suppose we mean by fine grain? Well, if you gave me some amount of silicon, like, say, a square meter, I might cut it up and make 9 little computers out of it, connected in a network like this. Or I might cut it up into much, much smaller pieces. By just ordinary usage and almost jargon, people have attached the term medium grain, or larger block size of nodes, to machines in which the nodes are roughly circuit board size, and fine grain to machines in which the nodes are roughly chip size, or several chip size. Somebody might say, what happened to large grain? Well, there are large grain parallel systems, machines like Cray YMPs and so on, in which a single processing element is something more like a cabinet than a circuit board. Of course, the relationship between what is a chip and how much you can put on a chip is changing constantly. So these machines also have a characteristic that they evolve over time. I'll get to that shortly. One more point about the basic structural architecture is that unlike machines such as data flow machines, in which there is a lot of policy built into the basic hardware, multicomputers are quite simple. That if you look at a multicomputer node together with its part of the routing network, this is what we might put on a chip or on a circuit board, you'll see that there's one part that is about the best memory we know how to build, another part which could be implemented as sort of the best processing we know how to build, and another part that is the best communication we know how to build. And all matters of policy are in the software. So we like to use the phrase, we provide mechanism, not policy. If you like data flow programming, fine. Program the machine to run data flow. These machines are relatively agnostic about the underlying computational model. Let me tell you, though, what we consider to be the base computational model for them. It's what we call the reactive process programming model. And I'm going to do this a little bit fast. Basically, what you mean, first of all, by a computational model is the terms in which you're allowed to express a computation. And here we'll express a computation in terms of two basic kind of entities. One of them we call processes, and this has more or less the same meaning that you're used to on a Unix machine. It's an instance of a program that can execute. And the other entities are messages. We call processes active in that they execute. They're principally stationary because we don't move them around needlessly. And they tend to be persistent. That is, they run to some sort of termination. Messages are inert. What I mean by that is that if they transform the data they contain, you call it an error rather than a feature. They're mobile, of course. They're the agents for carrying information around, and they're transitory. That is, as soon as they arrive at their destination and are consumed, you're done with it. It's very handy to use a reactive process in multicomputer programming, in which the process is normally at rest. The message is the token that allows the process to execute for some period of time. So if you think of a process as being dormant until a message arrives for it, that message then triggers off execution, which, formally speaking, is supposed to last for a bounded time. And during that bounded time, the process can do essentially three things. It can send additional messages. It can create new processes. By the way, those of you who are used to C++ kind of notation, of course, we say, I want a new instance of the process that has this definition, and I want to initialize it with this list of persistent variables, and new returns a reference to that process. So, of course, this kind of process reference that allows me to send some list of items to a process reference, and we very often key this to a particular method of the process. I'm using the word method here deliberately to invoke images of object-oriented programming as there. The third thing that can happen is that the process can evaluate expressions, do iterations, assign to its variables, and all of the usual kinds of things. And when it gets all done with those, it either exits, that is, it terminates itself, or it prepares to receive another message. If I can flesh that out just a little bit, some other points of possible confusion are that the variables of a process are private to the process, just as in, say, a Unix machine. It's not like a shared memory multiprocessor where variables can be accessed by more than one process. In a lot of places like MIT, where you might imagine Lenny and I spent a lot of time, not only did I spend a lot of time there, Lenny did too, which is why he remembers it so fondly. Around MIT you hear lots of talk about the namespace of the computation and things like that. Sounds pretty good, doesn't it? Well, of course, the namespace of these computations is a set of references to processes. A rather important and often neglected point is that all the processes that exist at once are concurrent. And they can be concurrent either because they reside on different nodes, or they can be concurrent because they're interleaved in execution on a single node. And as long as it was important in the development of multicomputers that this definition was accepted from the outset, because it means that in principle the semantics of the program don't depend upon how the processes happen to be placed. Another point, this is a place where the American version of multicomputers tends to differ from the Bohr's communicating sequential processes and Occam and the NMOS transputer definition, that all the American multicomputers use a scheme in which process execution and message transport take place concurrently. This has proved to be somewhat important to their success. And then there are some very minor points, such as the processes are able to, as we say, exercise discretion. Remember, they taught us that discretion is the better part of valor. And this is what we say when we talk about the characteristic that processes are able to receive messages selectively according to some characteristic of the message. In our usual reactive process programming scheme, we implement this by allowing a process to activate and deactivate one of these methods. So for example, if you send a message to a process in which a given method is deactivated, the message remains queued until the method again becomes active. So this is the whole story there. If you want more detail, there is about an 80-page chapter in this book edited by Tony Hoare that will tell you much more than you probably really wanted to know about multicomputers. Somebody told me a long time ago that it's always nice to invent a set of properties and persuade people that if I made a system with these kind of properties, it would be attractive and useful and so on. And on the other hand, it always helps to have an existence proof. So quite a few years ago, my students, staff, and I put together this machine. This is the 64-node Cosmic Cube we built in 1983. This picture, at least, was taken in 1983. And this is a manufacturer's dream. This is just a repeated copy of 64 identical circuit boards in a large card frame. Underneath this, there is a binary in-cube network, and each one of these computing nodes could communicate with five of its companions in this binary 6-cube. And one of the nodes in the middle had a 7th channel that allowed it to go out to that little host computer. This is now at the stage not of telling you what a multicomputer is, but to give you a little bit of background. That machine had 128 kilobytes of memory per node, 8 megabytes total. And the processor was a Intel 8086, about a 1/6 of a MIPS, very feeble processor. But it was enough to allow us to do some experiments, programming system development, and application experiments that persuaded some other people that this might be a commercial business. And sure enough, this is a 1985 Intel IPSC-1 multicomputer, which came in 32, 64, and 128 node varieties. By the way, I don't take responsibility for what any of these commercial multicomputer companies do. Particularly not for the styling of their boxes. These remind me more than anything else of 1950s style refrigerators. But this is what the node of an IPSC-1 looked like. And this particular business of medium-grain multicomputers moved along fairly quickly. Here's a machine that my group designed and licensed to Amatec for manufacture. This is one of our Caltech undergraduates. By the way, this undergrad is a normal-sized human being. This is a rather large machine in a normal-sized person. You shouldn't think that we got one of these very small Caltech undergraduates to stand there in front of the machine. And she's pointing at the light associated with one of the nodes that happen to have found a counterexample to a particular numerical conjecture, number theory conjecture, she was rather proud of. So this particular machine happened to have 16 nodes behind each one of these panels here. This corresponds to these 16 lights up here. And if you walked around to the back side of the machine and opened up the door, you thought Lenny was the only one who pulled this kind of stuff. You would see this. So this was the first of the second generation multicomputers. Used a routing mesh backplane in which this was a two-dimensional mesh structure. In fact, this is the top of one box and the bottom of another box. You can see the jumper cables that connect these, as it turns out, 4x4 boxes to each other. And similarly, they're connected over horizontally. So then Intel later caught on to this scheme, and Intel Touchstone Delta, which you may have read about in the newspaper, one of the contenders for the world's fastest computer, uses something that is very, very similar to the layout of this Amatec machine. 16 node boxes, 4x4 routing mesh backplane, and all of that sort of thing. So that's a part of the background. Multicomputers developed into an architecture that was demonstrably useful. And people learned how to program them and all of that. And we'll back up a little bit. Why did we ever bother with concurrent machines to start with? I mean, everybody knows that concurrent programming is terribly hard. And those of you familiar with the underlying theory of computation know that there is no real escape route to writing explicitly concurrent programs. That is, I can't get away with taking some sequential program and putting it into a magic translator that translates it into a concurrent program, simply because the sequential program, if it's efficient, may use an entirely different algorithm than an efficient concurrent program. And the compiler that can transform between algorithms in a semantically preserving way is way beyond anything we could imagine today, if not contrary to the theory of computation. So why did we bother with concurrency at all? Anybody have any ideas about this? Speed. The greed for speed is alive and well. Why can't we just build faster sequential processors? Yeah, there's speed of light, and there's a lot of other things that go wrong. Those of us who spend a fair amount of time fooling around with chips would give you the following perspective. This was a perspective that I think we fairly well understood even in the dark ages when most of you were in high school. First of all, starting in about 1980, there were a bunch of VLSI complexity results. These are the so-called AT squared bounds, where to perform a certain kind of computation, like binary multiplication, you could show that any implementation had a characteristic that the area, A, and the latency, T, of the computation were related such that the area times squared was equal to or greater than some problem-dependent and technology-dependent function. Well, it's actually the technology is a constant out in front and a problem-dependent function of the problem size. For example, for binary multiplication, AT squared is at least some constant times n squared for n-bit integers. That seems like kind of a dry and useless result. Do they rent apartments to people around this part of the town?
Not for anything we can afford.
Not just as we thought. Well, if you rent an apartment, it generally, what it costs you, say to rent it for a month, is proportional, or rent it for some period of time, is proportional to the area and the time. Now, if I want to use some part of a chip to do something like binary multiplication, my strong suspicion is that the cost per operation, if I can make reasonably full use of this little hunk of chip, is that it should be proportional to the area I'm using and the amount of time I'm using it. If after all the amount of time I'm using it is less to do this one operation, I could use it for some other hunk of time to do another such operation. So the cost per operation is sensibly the area time product. So if you believe these area time squared bounds, you have to believe that the cost per operation varies as 1 over t. A rather startling result. I mean, probably you thought it costs the same to do a given computation no matter how fast or slow I do it. But according to this, it says if I do it fast, I have to pay more. Small t indicates large price. Okay, let's look at the physics of this situation for a minute. There are a whole class of circuits that examine the limiting case of how little energy can I use to do a given operation. Now, energy is the usual physical metric of cost, of course. These so-called hot clock circuits, I can look at the very simple operation of I'm going to drive a signal transition onto a wire out here. And of course, wires and circuits have a certain capacitance. And if I can arrange for the resistance of this switch when it's tied, it's connected, to be small enough so that RC is much less than this transition time, then the energy required to drive the wire varies as 1 over t. Where did we see that before? Now you can show that there are lots of circuits that have this property. If you build a mutual exclusion circuit, a circuit that takes, say, nearly simultaneous requests and provides mutually exclusive ramp signals, if you're in a big hot hurry for that decision, it's going to cost you more energy than if you were willing to take longer time. A result that Dick Feynman first worked out. Here's an empirical observation. If you look at all of the contemporary instruction interpreting processors, those using the same technology, or if we can normalize to that, and we plot MIPS one way versus silicon area the other way, all of the good designs fall on a curve that looks like that. Notice that it takes a certain amount of area to make something that interprets instructions at all. Right, so there's nothing down here. But as we go to more and more and more area, we can get more and more MIPS, but it costs us more and more area to get each extra MIPS. So as this thing flattens out, in fact, as you get to a processor that's really big, it starts throttling itself. Because there are very physical limits of communication across it, so that this will actually droop down in the end. But obviously, we don't want to be operating anywhere here where the slope is less than 1, and because the computer usually has some other stuff besides processor, we want to pick processors out at this size. But we're still in a point of diminishing returns in performance per cost. So this is a result, empirical result, very much like the AT squared results. But because processors are not simple algorithmic engines like multipliers, it's very hard to do this kind of thing analytically. Now, a lot of you are graduate students or postdocs. I don't have to convince you of this. You know empirically that this is true. As your theory professors would tell you, computing cycles cost asymptotically 0 if you're not fussy about when you want them or how fast they are. At least I hope that's true around here. Like if you want computing cycles in the middle of the night and you're willing to take not your fastest cycles and inconvenient times, No, they don't cost anything. What people are really buying when they buy, when Lenny plunks down large bucks for computers for the department, and what he's buying is he's buying response time. And he's buying response time for the faculty and the staff during daytime hours.
You're getting me in trouble now.
Which means that at night, computing cycles are free. There's a bottom line to this. I don't really mean to make light of it, and a fairly important bottom line. If, in fact, you believe that the cost per operation varies as 1 over t, if I have a computation to perform that it can be formulated in terms of n-fold concurrency, and it's reasonably balanced, and a whole bunch of other caveats, such as there isn't really intense communication between these n parts. My claim is that I can perform, versus a computation that must be performed sequentially, or that is performed sequentially. I claim that using this 1 over t relationship, I can perform that computation either n times cheaper in the same cost, n times cheaper in the same time. Now, how do I do that? Well, I want to say I have this problem of I've got to do this computation in 1 second, or else the target gets away. And I can either do it with 1 billion multiplications, each one of which takes 1 nanosecond, and they occur one exactly after another. Or maybe the problem can be formulated so I can do 1,000 multiplies at once. Now, it might not seem to make any difference, but it makes a big difference. It makes a difference of a factor of 1,000 in what the computing engine costs. And that's because if I have 1,000 multipliers, each one of which can take a microsecond instead of a nanosecond, the cost per operation is 1,000th as much. Of course, you can do the same thing. This is the harder result to see, that if I want to go faster with a given engine, I can simply replicate it. In fact, it could be said that much of what computer architecture is all about in the late 1980s and through the 1990s is trying to see if we can get returns in performance for cost that are nearly linear, rather than these diminishing returns kind. And when people study caches, when they study pipeline processors and so on, what they're doing is studying various approaches to using concurrency to achieve performance rather than using all-out serial speed.
Computer. I didn't understand the 6-equal calculation.
You didn't understand what?
Yeah, if you take the time to be longer, before you call it down, then you have to do in parallel. You need few computers to keep the cost of these new computers. So, I mean, n times 1 over t divided by n is 1 over t.
Look at it this way. Sometimes this argument is too direct for people to understand. Because I've given it to you right off in terms of the cost per operation. Now, if you're a real hardcore engineer, what you will notice is that if I am allowed to make a multiplier that is, say, 5 times slower, it's going to take 1/25th the area if it's AT squared optimal. Does that help?
Yeah.
Okay. The one other thing you should notice is the larger n is, the better. Right? If you believe don't go after small gains, go after large gains, let's go after large n. I showed you these pictures before of some of the machines that people have developed since the Cosmic Cube. I'm very sorry that this is a busy slide, but it will leave this for you to think about for a minute. We'll use this one. Isn't this wonderful? If I switch them again, the cameraman would be completely out of it. This is one of these tricky log-log graphs. So you know right off, I'm trying to pull the wool over your eyes a little bit. Factors of 2 on this graph are roughly the size of one of these dots. So I'm allowed to be quite imprecise. What I've done here is I've taken a number of machines, each one of these is a black dot, and plotted it here. And these machines are from quite different time periods, starting with the 1983 Cosmic Cube out here. And then I took all the Intel machines, the IPSC-1, IPSC-2, the IPSC-860, and the Delta, and the announced Paragon machine. And it appears that Intel is following what we call a scaling track along here. Now, for each of these machines, I plotted them according to what their performance is in operations per second per node. I'm really just plotting the characteristics of a single node. And I'm plotting the cost per node here, but because people like to think of better as being off in that direction, I've done this by making up a hypothetical $4 million configuration and saying how many nodes could I buy with that. But those of you who know what's really going on can just look at the cost per node in red here on the left. So indeed, what Intel has been doing, by the way, I'm not cheating either. Things like the Cosmic Cube nodes cost us a little over $1,000 a piece to make. But I'm listing them as $4,000 because I'm scaling all experimental university-built machines by a factor of 3.5 per node to represent the manufacturer's markup. The prices for these Intel machines are the best that I know of, and the performance is the best estimate I could make. Anyway, after the Cosmic Cube, Intel introduced these machines. InCube introduced the machines that would have fallen on more nearly a constant cost scaling track. But you notice that the aggregate performance, which you can read on these hyperbolas, now hyperbolas on log-log plots are straight lines. So these are hyperbolas of constant aggregate performance. Here's the magical teraops. It's 1 billion operations per second, 100 billion, and so on. You can read the values back here. So a machine like the Cosmic Cube did a bit over 100 million operations per second, as you can see here. I'm sorry, there's something. There is a mislabeling problem on this graph, and I'm sorry about that. It's correct. This is as if it were a 1,000 node machine. So indeed, a 1,000 node machine would have done a bit over 100 million operations per second. These successive Intel introductions seem to be cutting across this constant aggregate performance rather obliquely. And in fact, the size of the nodes has actually been getting bigger. That was not at all what we had in mind with the Cosmic Cube experiment. And to convince you of that, here's the first page of a January 1985 paper from the Communications of the ACM, where it says, up here that the Cosmic Cube computer is a hardware simulation of a future VLSI implementation that will consist of single chip nodes. It says more or less the same thing down here. Hardware simulation is what we expect to be able to integrate onto 1 or 2 chips in about 5 years. Why would we want to make the nodes so small? See, what was the moral lesson from this? If you really have the greed for speed, go for large N. I'm not going to claim that these machines are useful for everything. These are useful for case applications in which the concurrency is abundant. But if the concurrency is abundant, you ought to be able to run the computation more cheaply or get more bang for the buck out of a machine with larger N. So indeed, you see what's happening with this kind of machine is that they're actually scaling N down. Whereas with machines like the Mosaic, which go to single chip nodes, that's a nearly constant complexity scaling, in which we're using the technology to make the nodes faster, which we can use, and cheaper, which we can also use, and use less power and less space and all of that. Okay, well the claim over there is single chip nodes 5 years hence, and that says January 1985. So where are they? Well, there's one. And indeed, compared to the cosmic cube nodes, these are 60 times faster. They cost about 25 times less, 25 times cheaper, about 1/100th the volume. They use about 1/20th the amount of power. Now, if you look at performance per cost, I said these are 60 times faster and 25 times cheaper. So this machine is about 1,500 times better performance per cost. Isn't that remarkable? In only a decade, you could, the base technology gives you a factor of 1,000 in performance per cost. Of course, we are comparing a gorgeous Caltech design with a fairly crude Intel design, but and consistent with this factor of 1,500, if the log base 10 of 1,500 is about 3.2, so sure enough, you notice that the Mosaic C appears 3.2 decades above the cosmic cube, and fully factor of 10 higher performance per cost than its contemporaries. Because what is it shooting for? It's shooting for 16,000 nodes instead of 500 or 400 or numbers like that. Here's a little bit more. This is a pretty color picture of the Mosaic node. What you're actually seeing here, this lower part is the primary memory, 64 kilobytes of memory. This is like the computers that Lenny and I grew up with. Right? Well, I remember a PDP-9 used to, what was it, Danny? 32K 18-bit words and something like that. I mean, these, but of course, these are a lot cheaper and faster and so on. And this is the instruction interpreting processor up here. This is the packet interface. This is the read-only memory. This funny-looking thing here is the clock driver. And over in the corner there is the packet router. So if we take a more conventional view of that single chip node, you can read the statistics off yourself there, if they're of any interest to you. There is a statistic that's kind of interesting to me. It's 61% of this chip is the primary read-write memory of the area. More than a quarter of the chip is devoted to communication. That is the pad frame, the connections to the outside world around the edge, the router, and the packet interface. The processor is only about 3% of the chip area. You could obviously double the size of the processor without impacting the chip area greatly. But only doubling the size of a processor these days doesn't give you much performance advantage, because you're operating in a regime operating in so much of a regime of diminishing returns in performance per area. By the way, it's not unusual in something like one of your local workstations for the processor to represent only 3% of the silicon area, and for the primary memory to represent 60 or so %. So this is not a shockingly different computer in any respect, other than that it devotes so much area to communication. Okay, now comes the relaxing part. Nothing much to think about. This was a lot of hard work, but it was a lot of fun too. What do we do with these chips? Well, obviously they are designed to be arrayed. So that was one of the early test boards that we made for testing the chips realistically. The people building the atomic network used these things as switches. But this isn't a very exciting way to package it. So how about that? That's actually actual size. This slide was made by that's a this color copier slide by putting one of the boards at 1x magnification on the copier and running a copy. You have a question?
The slide is life size or projection.
Yeah, very good. Now you might say, gosh, how do we tack the chips down onto those little tiny spots? Well, there is a way to do that, which is called tape automated bonding. And here's a picture of the backside of one of those Mosaic chips. You don't mind if they see a little technology here, do you?
If you must.
Okay. But the trouble is, this gives away the secrets up here because you can see who did it and when, and you can see their part number for it and so on. HP has been our subcontractor in the development of this stuff. You can also see HP's logo right there, and the HP part number, if you could read it right there, for the board. Good example of such cooperation. Now, this middle part is the back side of the chip, and see these sprocket holes? This is why they call it tape automated bonding. It's meant to go in a sprocket feed like 35 millimeter film, except this happens to be 45 millimeter. And each one of these points after the chip is interleaved bonded down to the tab frame. Notice it's brought out to these test points so that you can test the chip after it's been packaged. And then the next step takes capital investment of a few $1 million. These pictures were taken at MCC, the Microelectronics and Computer Corporation in Austin, Texas, in their packaging operation, where this machine, this robot, staples the chips down onto these boards. And after they're put down onto the boards, they're put into a tester that is actually just an operational Mosaic system running normal system tests. And of course, inevitably, one of the chips fails to get bonded correctly, or it fails to, it's been cracked, or some horrible thing like that. And so then they have to have another machine, another robot, that goes down and picks off a defective chip and puts down another good one. So that's the picking off machine, and here's the putting down machine. And oh, these robots are great fun.
You said the chip was stable. How is it actually mounted on?
It's actually done with thermo that goes around the outside, and the board has a solder coating, so it is actually soldered down to the board. And what we end up with after all this is over with is this is an artistic photograph of one of these boards all finished with this 8x8 array of chips on it and some connectors that connect onto the edge. Now, I've already shown you that other picture, but do any of you have any idea why this board has such a strange shape? Why are the corners here notched? This is not maybe as good a picture as this one I showed you before. Have you ever seen a board like that before? Anybody have an idea why it's done like that? All these atomic network guys are quiet now. play with these all the time. Well, of course we can use the edges to connect other things, but these boards were made to be self-composing. Because in the same sense that the Mosaic chips are made to be arrayed, once we have a board like this, the boards in turn are made to be arrayed. And so these connections on one of these edges, like the top, of course, neatly mates with the ones in the bottom. When you do that, however, they're vertically offset from each other, so you have to stack them in some sort of arrangement like a checkerboard. So sure enough, when you do that, you have to have the corners notched out, or else these would physically interfere with each other. Now, I want you all, when you show your grandchildren computers that are put together this way, I want you to tell them, I saw that back in, and I don't think this is going to be a permanent feature of these kind of machines. I think they're going to end up being more like the HAL 9000 type, where they have little motorized things that you can push the modules in. This ends up being a little bit too tedious for day-to-day repair work. Well, what we end up with here, of course, is quite a neat little computing engine. It's about 16 inches on the side. If there's 64 kilobytes per node, 256 nodes here, you can all multiply this out and get 16 megabytes of memory. If it's 11 MIPS per node, you can multiply it out and get a peak instruction bandwidth of about 2.7 giga operations per second. Not bad at all. The nodes take about half a watt each, so this particular machine is about 120 or 130 watts. So in terms of execution bandwidth, 22 mega ops per watt is quite unusually high. The communication channels in this machine operate at 60 megabytes per second. So this little desktop machine, as it were, has a higher bisection bandwidth than the Intel Delta at Caltech, which uses the same routers, but can't source and sync packets nearly as fast as these little computers can. It has a higher, several times higher bisection bandwidth, bisection across here, than a CM2 or a CM5 or practically anything you'll see around. And why is this? Well, it's basically because a fine-grained multicomputer can't be designed as just a scaled-down version of a medium-grained multicomputer. That when you make the nodes smaller, the processes become smaller, they become more highly interdependent, they have to send messages to each other more often, and so the parameters of this machine were drastically adjusted accordingly. Let me show you one other thing about this that completes the system. Here's a plot of the production version of the Mosaic chip, and if you look kind of carefully for a minute at the processor, packet interface, clock driver, the scale of the clock driver here, and this is the router over in this corner. Well, because of the Moses service, we can take these same pieces, that is, everything that's on this chip, and take away the read-only memory and the read-write memory, wrap a different pad frame around it, and presto, this is a different scale chip. Instead of being about a centimeter on a side, this is about half a centimeter on a side. So here is what we call a memoryless Mosaic chip. For that matter, we can do this one more step, and get rid of all of this stuff and have a chip with just the router. And in fact, we've been providing these routers to about a dozen different projects throughout the United States for machines like the Stanford Dash multiprocessor, several of the parallel processing projects at CMU and MIT and Mississippi State University and MCC and at several commercial companies all use routers that are basically derived from this one. So this was our opportunity to have a little bit of a spin-off effect other than the project itself. Okay, given this particular chip, we can build multi-computers. In fact, I'm sort of turning the story around because here is a 2-node. You know how to find it in this maze right here. This thing right here is a 2-node multi-computer. And those of you who like to open up the backs of your Sun workstations will recognize that this is a Sun S-Bus board. These are memoryless Mosaic chips. These are the external memory, and that external memory can be read or written either by the Mosaics or by the workstation. So here we have an interface between the workstation world and the Mosaic arrays. And thanks to our co-workers that working on the atomic network, they suggested a good way to do this is with an arrangement such as this, where the Mosaics, which do an X first and Y routing, sway from, say, one node that's out in the host interface. The host interfaces can be chained, and I can, say, go some number of steps in X and then some number in Y, and get to any node in the array. Likewise, from any node in the array, I can make some number of steps in X followed by some number of steps in Y to get to any node out in the this linear network. Again, I'm corrupting history notoriously here because we didn't do it this way to start with. But after providing the people at USC ISI some hardware and programming toolkit, I believe it was in August '91, about a month or two later, they had an operating local area network based on these components. This is a story that if you want to know more about it, you know, ask Danny or Greg or Feldy. See, to these guys, they said, to what the Mosaic is it's host interfaces. These are the basic modules. It's these in-by-in switches, like these 8x8 boards, or that's a 16x16 switch. And it's cables that hook them up to each other. And if I want to make a network, I might do it like that. These are, by the way, Danny's slides, so I can't be responsible for these ugly sans serif fonts and various things like that he's fond of using. So in this picture, you could think of each one of these as being a workstation. You see, to the network people, Buzz, the switch is the important thing, so they draw them big. These are the workstations out here. And these can be chained, you know, into a switch. So if I wanted to get a packet from, say, here over to there, I might route it into this switch, which sends it up to this switch, which sends it over to there. And in actually the native Mosaic channels operating at 30 megabytes per second, I guess that's 480 megabits per second. So this number here is an exaggeration. On the other hand, all the following numbers come from measurements. This is their status as of April, because I couldn't find the slide that says what their status was after a full year. They've worked very hard to get the world land speed record for almost everything. I don't know, how many networks do you see, Lenny, that measure performance in megapackets per second?
Many today.
Yeah. Of course, these are very short packets. And this is a very local area network. And, you know, basic channel bandwidth, inter-host bandwidth. And this number right here is that, I don't know if these guys are being completely honest about this. I can believe it based on our Caltech experience. But they say whenever it's working, our error rate is 0. You have to kind of wonder about the scientific validity of a statement like that. But they, you know, seriously, when they, unless they've found some reason for an error, like somebody's unplugged a cable, they are now well over 1 petabit of information transferred without a single error. So this is an example, atomic is an example of one of the two kinds of applications that we had in mind for the Mosaic. That is, the Mosaic was not aimed exclusively at teraops computing. It was aimed partly at that because, if somebody has a race, we might as well join, right? And there's no CHP to tell us not to do it, and there's, other people who are goading us on. So, sure, we might well do that, but it's not too interesting to me, frankly, that there may be 1,000 or so supercomputers in the world at some point. Because after all, there are millions or hundreds of millions of small computers around. Not to mention all of the gadgets that we use to support networks and our appliances and everything else. So in many respects, the embedded systems applications of the Mosaic are a way of getting the performance per cost advantages you can get in really tiny nodes into smaller scale computing applications. That is, you don't have to be a national lab to use one. Okay, now I'm going to tell you just briefly about the programming system. Lenny's secretary, Natalie, has a set of 3 papers that any of you are welcome to go to Natalie and copy about the design, sort of overview paper, and one about the details about the hardware, and another one is a detail about the programming system. But basically, this programming system is quite different from anything we've attempted before. In 2 ways. One of them is that because the processes are small, the natural brain size and execution is small, and it had to be practical to be able to express concurrency at the scale of functions or, say, methods of objects rather than operating system processes. When you're down in that particular scale, it is much more practical and much more elegant to express the concurrency within a programming language rather than to sort of tack it on to an existing programming notation. Well, fortunately, the C++ had developed to the point that made it quite tractable to modify it, to extend it, to make a quite decent programming system. We had, for a long time, envied the CSP and Occam work of Tony Orr and company in that they were able to express their programs lexically together. For various pragmatic reasons, with the Cosmic Cube and its commercial descendants, we took existing programming notations like C, added a set of message passing and process creation primitives. You compiled the processes separately. There was no way to know whether a message received was conformal, type conformal, so to speak, to what you expected. It was really kind of a crude system in many respects. Whereas the CSP people were able to express their programs lexically together. And they could compile them. Unfortunately, they had a view of programs that was rather static for my taste, and I think for the taste of the faculty here. That is, the set of processes and their connections had to be, in effect, denoted ahead of time. We much preferred to write programs in which processes could create other processes in execution, could pass reference, and so on. A rather freer, more libertarian kind of system, you might say. We also wanted the advantages of being able to do a lot of checking at compile time that we had previously had to do at runtime if we were able to do it at all. So anyway, we start with one of these C++ source programs. That's what we call it right now. It goes through what is modestly called a translator. This translator was written by one of my graduate students, Seitz, to, for practical reasons, produce C++ code that then is compiled by G++, the GNU C++ compiler, and linked with a library that some part of which is machine specific and other parts is general, and then finally produces an executable program. How many of you know C++? All the graduate students. For those of you who do, I'm going to leave this up here for a minute and you just get the general flavor of it. the essential idea is that whereas C++ has class definitions and instances of classes or objects, C++ has those same things, but in addition it has a process def construct. Process defs are just like classes. They have inheritance. The full syntax and semantics of C++ is supported, except that there are no global or static variables allowed. Processes are created with the usual C++ new. Message sending is done once you have reference to some process like m. If you invoke some function f of m with an argument list that sends a message. It sends the message I with the selector f. Of course, there isn't really any such thing as message receiving, because these are reactive process semantics. It's just whenever a message is received, it runs the appropriate function, and if that function is active. And you can make functions active and passive with these simple calls. That's all there is to it. You notice that syntactically processes are like, process defs are like classes. Semantically, processes differ from objects in an important way, which is that when you invoke some function of an object, you expect the immediate action that's characteristic of sequential programming notations. When you invoke some method of a process, or some function in a process, you get a delayed and independent action. And that's characteristic of concurrent programming notations. Our overall evaluation of C++ so far is that, particularly compared to some of these earlier systems, very efficient. About 10 assembly instructions per message sent or received. By the way, that compares with 400 to 800 on your typical medium grain machine. And of course, things like inheritance and features are, C++ uses static inheritance, static overloading, things like that. If you use them, you pay a little bit for them, but if you don't use them, you don't pay for them. Nice characteristic. We've written a lot of programs in C++. You see all of the usual object-oriented features are there. And what is the test that C++ is expressive? Well, the runtime system that runs on the Mosaic is written in C++. That's a system program kind of thing. And on the other side, fairly serious application programs ranging from game playing to numerical computations and so on are likewise written in C++. It's always a very treacherous thing devising programming notations, because you're treading a thin line between expressivity on one side and efficiency on the other. And so it's oftentimes difficult to predict without doing the experiment, whether the language is going to show a good combination of expressivity and efficiency. Some of the things that we've done in the runtime system are equally different. There are what I like to call skeletons in the closet in the runtime system area. On medium grain machines, you typically have to place processes yourself. You specify which node to create a process into. If you overloaded a node by too many processes or too much, or the receive queue overflows or something like this, you get a message saying, sorry, can't proceed, I ran out of memory in node number 377. Tough luck. Rajiv Bagrodia and his students use one of our Simul S2010 or Amatec S2010 machines over at Caltech, and I'm sure they're very familiar with this message. Do you get this from time to time?
Yes.
Yes. And there are reasons why we wouldn't want you to get this message with a Mosaic. Because you see, when you get it on the Amatec machine, it's your fault. Because it was your program that placed the processes and did all of that kind of thing. And furthermore, it's unlikely because the nodes have quite a lot of memory, like 4 megabytes per node. On the Mosaic, if you get that message, it's our fault. Because we placed the processes. And we're trying to manage all the resources in the machine. And what's more, a fluctuation of a few thousand bytes in something like a receive queue may be enough to cause the program to terminate, even when it may be that 3/4 of the primary storage in the whole machine is unused. So if you've been reading some of the points in this slide, these are skeletons in the closet that we would dearly like to get rid of. And there are solutions to all of these. For example, the receive queue overflow. If we have extra storage left in the node, we'll take a part of the receive queue and export it to some other node for a while. There's a question about, do we have to have all the code everywhere? Probably not. And the present runtime system uses an LRU type of scheme for deleting unused copies of code. But there's still another way to deal with this. If you have a message that has to be run with such and such a function, the obvious way to do this is to go get a copy of the code and bring it to the node and execute it. But usually the code is bigger than the argument list and set of persistent variables. So why not send the process, that is its persistent variables and the message list, off to some node that has the code and let it be executed there. And we're getting surprisingly good results doing things like this. Okay, so there are a lot of experiments. The Mosaic C is in fact kind of an experimental vehicle for trying to figure out what kind of process placement techniques work well enough, and we knew that we could build a machine and all of that, but there were a lot of questions that we just didn't have answers to when it came to what percentage of the memory can we use when we don't insist that we use 100.0% of the memory, but if we could use 95% of the memory of the machine before the computation bogs down, or even 85%, we'd be exceedingly pleased. Okay, one final point. Where are we going? Well, of course, Mosaic C is going to be followed by another one, and it's called Mosaic T, where T stands for teraops, and that's, of course, a good sales term these days. This is, of course, an already, actually long ago, a couple of years ago, proposed and funded project, and we are expecting about next summer to see the first silicon on the Mosaic T chips. This is a machine that is a lot like the Mosaic C, except that we've learned how to design better processors in the meantime. And this is targeted for a somewhat smaller feature size technology, 3.3 volt operation, still about a ½ watt per chip. And so one of these, we also have seen the desirability of increasing the memory bandwidth on the chip, simply because we've been able to push the communication bandwidth. Our existing 60 megabyte per second routers that we distribute to a lot of people are actually old technology. We have 200 megabyte per second routers. Indeed, the internal speed of our routers is more like 330 megabytes per second. It's just that it gets difficult to handle that on package pins. So this chip is built around a few basic numbers, 200 megabyte per second channels. If you want to be able to send and receive packets concurrently, you better have about 400 megabytes per second of memory bandwidth, which means that you need 2 banks. One other difference is this chip has an interface to secondary memory. If you look at what one of these Mosaic chips costs versus what memory costs for your Macintosh, you're disappointed, because the memory for your Macintosh costs about 1/10 as much. So we obviously have to have some way of using commodity dynamic RAM memory. So we, of course, do this on some secondary bus.
Do you widen the bandwidth of the channel by upping the clock or widening the path or both?
It's good. We can do 200 megabytes per second on an 8-bit path.
So 200 megahertz clocking is what
It isn't clocked, it's all asynchronous, but it runs at least those rates. If we run it 16 bits wide, we can operate at 400 megabytes per second. There are, of course, several control signals associated with these.
but it's asynchronous, it's not clocked.
It's asynchronous, or you can say that the clocks are emitted from the chip that is emitting the message. Once you have, this bus here is nominally 32 or 64 bits wide. Once you have secondary memory out here, there's nothing that prevents you from putting secondary processors. Then you end up with a very interesting structure. We call it a 2-level multicomputer. And at this point, we can brag a little bit that 5 or 7 years ago, we had already understood the desirability of this structure. And using the Mosaic T in effect as the communication engine and to run the operating system. There isn't anything that we can do in these secondary processors that particularly needs an operating system. We can use very performance-oriented chips like digital signal processing chips running at, say, 200 to 400 megaflops out on this secondary bus. You say, well, how do you program it? You all know about basketball here at UCLA? I hear you have a basketball team here. You know the standard thing in basketball when there are two players dribbling down the floor side by side, one of them can just shoot it. So in reactive process programming, if this Mosaic gets a message and it's directed to the Mosaic, it might just execute the message. That's what we think of in reactive process programming. On the other hand, it might dish it off, as they say in basketball, to the other player. One of these secondary processors down here, fast break maneuver, of course the tag on the incoming message tells you where to send that. That's, by the way, one of the reasons why we changed the semantics slightly from arbitrary types to an explicit method lookup, because it's necessary that the Mosaic be able to do all of the dispatch. And there's no guarantee that the Mosaic could even operate on the same data types as the secondary processors. So you notice that this is a truly split computation in which the Mosaic can run the operating system, runtime system, all the communication protocols, and the outer shell of the program, so to speak. And the only thing that runs down in the secondary processors are, functions that certain functions that the user program coded. So, of course, this outer machine in green, that computer runs C++. But when it wants to do a dish off, it simply writes into a queue in the secondary memory. And these secondary processors are running a miniature version of what we call a reactive kernel, which is a simple dispatch loop. Get the next task, do it, get the next task, do it. So you see, as an experiment, we did things in the Mosaic C to answer the questions we felt we needed to have answered before we could go off and make a machine like this. Many of those questions were related directly to the runtime system. So at this point, I'd be happy to take any of your questions. And any of you who would like to escape, please feel free to do so.